my presentation, so make sure you talk really loud, all right? Okay, so my topic is glacial response to earthquakes. So here's my outline. I'm going to give an introduction to why I chose this topic and what my project basically was. I'm going to go over the research, the things that I had to, the variables and parameters I had to find, and how I got those, how were my assumptions and limitations, the methods and equations I used, finally what I found, and areas where we can do future research on this topic. So I got interested in earthquakes when I was on my mission. I lived through an earthquake there in Chile. There was a magnitude 8.9 earthquake, and it just totally destroyed basically everything. And we spent months doing service. I learned a lot about earthquakes, and I became very interested in them. For my, what I researched was I measured 3 glaciers that are near earthquake zones. And I I solved for length as a function of shear stress, and I plotted that. And the question I wanted to answer was, how does a glacier, how does its length change in response to an episode of an earthquake? For research, the first glacier I chose was one in Patagonia, Chile. Here's its parameters right here. Its thickness, 170 meters, maximum height, 2,700 meters. I calculated the ELA and the average slope and the maximum height using Google Earth. I also chose the Franz Josef Glacier in New Zealand, and one of the larger glaciers in Glacier Bay, Alaska. And they all had different slopes and different equilibrium line altitudes and different thicknesses. For earthquakes, I chose 3. The 1964 earthquake in Chile, magnitude 9.2 with a vertical throw of 8 meters. I chose the Wairarapa, New Zealand earthquake, documented by Charles Lyle. This was a vertical throw of 6.4 meters. And then the 1960 Alaska earthquake had a vertical throw of 13.8 meters. The vertical throw is what I use in my equations to estimate how much the length will change. The assumptions I made is I assumed that the entire glacier rested on the footwall of the fault. And so I didn't account for whether the fault was in the middle of the glacier or anything like that. Also, I didn't account for horizontal displacement. When I researched the earthquakes, there was a vertical displacement and a horizontal earthquake, or horizontal displacement, and I just ignored the horizontal for this model. And there were 2 glaciers, the one in Chile and the one in Alaska, that had calving at the end, which I didn't take into account either. And this is estimating how much it will change, but it doesn't tell you how long it will take for that change to happen. The methods I use, here's the equation for shear strength. This is a tau, which is shear strength. We've got the universal constants for ice density and the acceleration of gravity. Hm is ice thickness, and the slope, dH/dx. What I did is I calculated this with the values I got from Google Earth on the glaciers, and then I added in vertical displacement with the change in height, and I got a new shear strength for after the earthquake. Then once I had these values here, tau, or shear strength, and the new shear strength after the earthquake, I plugged these into the equation for length. And I had to also bring in, so here's a new tau right here, the new shear strength, and I also added in the vertical displacement for slope. So delta H plus VD over dx. And so once I did this, I had the old length and the new length, and I had the old shear strength and the new shear strength, and I was able to see how shear strength and length are related during an earthquake event, how those change. So what I found, I took the data that the computer program calculated, and I made this table. The question it answers, how does glacier length change in response to uplift? And here's the part I want you to focus on. Changing glacier length. In this Chilean glacier, the length changed by over 100 meters. It was shorter by 100 meters. In the New Zealand one, it was by 20 meters, and in Glacier Bay, Alaska, by over 300 meters. And this was only in response to a very small amount of change in the slope. So when the earthquake lifted the footwall up, then the slope became greater, and because the slope was greater, the strain rate had to, or sorry, the length had to shorten. Here's my plots. I've got slope against length, and this makes sense because when you increase the slope, the length where the glacier is actually at a stable temperature is less. And it was the same thing in all three. They all had this negative correlation between length and slope. So when slope increases, length decreases. Future research. I think it'd be really awesome for somebody to, and maybe I in the future could do this, explore effects of horizontal displacement on shear stress. So how does the horizontal component of the earthquake actually change what happens to the length of the glacier? Also predict how long it will take for this to happen. So my calculations estimated how much it will change, but I'd like to know also how long does that take. Also, factor in different fault locations, whether the fault is in the middle of the glacier or underneath the glacier or below where the glacier ends. And then also account for calving on the glaciers that had calving on the end. So that's my research. Are there any questions?
All right. Questions for Michael?
Yes, Doreen.
I had a question. It just blanked on me as I raised my hand. It is about, and so the final answers that you got on the lengths, the changes in lengths, have you seen or do you know if there's any data that you could, because these are all historic earthquakes, right?
Yeah.
Is there any data that you might use to help kind of see how close your model actually is to predicting how much they actually did change?
I haven't looked into specific other studies of that same thing, but I can tell you that my model is a little bit high because it takes the average slope from the lowest point to the highest point, and some of the glaciers they kind of wind a little bit, and so it doesn't take into account the measuring on that wasn't perfect, and so the length is going to be a little bit less than what it was in my models on most of those. I mean the change in length. Sorry.
Okay.
Thank you. Any questions?
I have a question. So when you're adding the fault throw to change the slope, right? Is it changing the slope tilting like this, or is it just raising the entire thing up like this?
So I took just 2 points. I took the from the top of the glacier and assumed that point was lifted up.
Okay. So it's changing the
Yeah, so the height would
lowest point is
change,
the same.
and because it's higher at a higher elevation, the slope is also different. But yes, sir.
What is your main conclusion?
So my main conclusion is that I'll go back to it right here. That an increase so when there's uplift in response to an earthquake, that glacier slope increases and the length decreases.
So I think another suggestion for earthquake is
Okay.
to use 3 different earthquakes.
Yeah.
And so did you check if which of the event is kind of different height, like the normal fault, or it's the frost event, or it's striking split?
And what I read, it just said that it was there was uplift, so I didn't look to specifically whether it was a thrust or a reverse or normal fault. That is something I would like to do in the future, though. Thank you.
I have a question.
Yes.
So in the equations that you're using the steady state glacier model, right? So one of the terms that rolls in here is this head of the glacier, and this follows from what Josh was asking. So you took the head of the glacier and bumped it up because of the displacement. So did you adjust the elevation of the head of the glacier
So
when you did that?
Yeah, the first time I made this model, I added the vertical displacement here and here, but it didn't change the model at all. And so what I did was I put it into the change of slope.
Yeah, so just looking at these equations, do you have a sense for why it's so sensitive to slope?
I think it was slope. Let's see. I think that I'm not 100% sure. I think it has to do with the slope being like on the denominator of these.
Yeah, so go back to your previous
Okay.
slide. So here you're showing us how it may affect the shear stress,
Uh-huh.
right? But on your next slide, what you're essentially showing is that slope actually comes in 3 different places,
Okay.
right? Shear stress, but then it also plays into other parameters in the length of the
Okay.
glacier, right?
That's an excellent point.
And it's the combination of those.
Okay. Thank you.
So, other questions for Michael? I have one more. Will you go to your table for a second?
Yeah.
So the absolute magnitudes in that length change, 100 meters, 300 meters, tens of meters, looks pretty large. Did you try doing the percent change? Because here you have a 33-kilometer glacier,
Yeah.
right? Is 100 meters relative to the length of the glacier? Is that a very big change? Do you understand the
Yeah, yeah.
question?
I understand the question.
So if you divide 100 by 34,000, it's a fraction of a percent of the
Uh-huh.
length, right?
That is a really good point. I should have put that into my Excel table.
Well, one of the reasons for doing that, right, and what's nice about this is you're using glaciers of different sizes, but you also have different amounts of uplift or change to the slope. You can normalize the response to the length of the glacier just by
Okay.
doing the percent change.
I think that's a really good idea.
Right,
Thank
so
you.
you kind of helps, you get many variables, right? But
So
what
you
you're really interested in
eliminate-
is how much does uplift affect glacier length?
Okay.
So it helps eliminate one of those factors.
Yeah, that's a really good idea.
Does that make sense?
Yeah.
Other questions for Michael? All right, Reagan, let's give
Thank you.
Michael one more hand.
If anybody has questions, more questions, you can see me after. Got it. So.